Now we will learn about the sampling distribution for counts and proportions. So binomial settings, the characteristics of binomial settings are there would be two outcomes, that is success and failure. Success is the category of interest, and the other examples are like defective or acceptable, deceased or not deceased, agree or disagree, true or false. So in short, there will be two outcomes. Number second is fixed number of trials are there. So you have you will know that how many number of trials will be there. And number three, trials are independent. As you know, it means that outcome of one trial does not affect the outcome of the other trial. Number four is probability of success. That is the P is constant for all n trials and P is a population parameter. Binomial random variable x, that is discrete. X is equal to number of successes observed in the n binomial trials. N is the fixed number of trials. And the probability on x are computed using the binomial formula. So to remember the binomial settings, we can remember it by word bins. So first is binary, that is the possible outcomes of each trial can be classified as success or failure. Independent, trials must be independent, that is knowing the result of one trial must not have any effect on the result of any other trial. N is for number, the number of trials, that is n of the chance process must be fixed in advance. And S, that is the success. On each trial, the probability P of success must be the same. So now we will see some examples and we'll see if they are satisfying the requirement for the binomial settings. So first is the number of defective light bulbs in a batch of 1000 light bulbs. First is two outcomes. So it's satisfying as there is two options, defective or not defective. Number n is fixed, number of trials are fixed. So we have already known that there are 1000 light bulbs, so it's fixed. Trials are independent. Yes, they are independent. And P is probability is constant. As the probability of one light bulb being defective, same as any other light bulb defective. Second example is number of broken eggs in an egg carton of 18 eggs. So there are two outcomes. Yes, either broken or not broken. N fixed. Yes, we know there are 18 eggs. Trials independent. No. P constant, no. Why? Because there is a good chance that if one egg is broken in a carton, then other eggs can be broken. And we can get confused it by the number of defective bulbs, but in the bulb situation, we are not talking about the if they are broke or not or something like that. These are defective. So sometimes you use bulb and they can be defective. But here we are talking about the eggs are broken. So now we know that it's not satisfying option 3 and option 4. So we cannot use binomial distribution for this example. Now the example is number of calls you make to a ticket agency to get tickets for a concert at the time they go on sale. So first option is two outcomes. Yeah, it can be possible that you make a call, it can go or cannot go. We can take it as yes. And second option is the number of trials are fixed? No, because it's not showing how many people are going to make calls or how many attempts you can make in making a call. So it is not satisfying option 2. So example 3 is not an option, not satisfying the characteristics for the binomial settings. Number 5 is number of flights that depart on time out of 20 randomly selected flights. And they are, it's also telling that there's same departure and destination. All the 20 randomly selected flights are having same departure and same destination. So two outcomes are there, that is on time or not on time. Number are fixed, that is 20 randomly selected flights are there. Trials are independent. Yeah, trials are independent as we can understand. And P Constant? Yeah, probability is constant here. Now for the last example, I will suggest you guys to go through it and will try to understand if it will, because we already know answer is given, it's saying no, but why it's no, you can understand it. And now the population proportions and probability. So population proportion is a fraction of the population having the characteristics of interest. Examples: fraction of patients in a hospital with type O blood, fraction of computers at a repair shop with failed motherboards, fraction of registered voters who actually voted in the 2008 presidential election. If each individual in a population is equally likely to be sampled, that is, probability of randomly selected individual has characteristics of interest, that is equal to population proportion having characteristics of interest. So here the probability is equal to population proportion. So sampling distribution of a count. So if we have very large population with proportion P of successes, first we take an SRS of size n, and second count number of individuals with characteristics of interest. X is equal to count of successes in sample has approximate binomial distribution. Why? Because individual either has characteristics of interest or doesn't. For example, if someone has O positive blood or not. So they are satisfying this condition. Number n, that is sample size, is fixed. Third is population is much larger than sample, so probability of success is almost constant on each individual. Fourth point is sample is simple random sample, that is individuals are independent. So here we can say that the count of success from SRS, that is simple random sample, has an approx binomial distribution. So here are a few examples. First is number of plants that die after applying herbicide to 50 plants. Number of Hispanics in an SRS of 1000 people. Number of parts that are defective in a random sample of 20 from a shipment of 14,000 parts. Number of students who carried an umbrella on a rainy day in an SRS of 150 students. And number of voters who favor a school bond levy in a random sample of 500 registered voters. So binomial distribution. Consider tossing a coin n times. Each toss gives either heads or tails. And knowing the outcome of one toss does not change the probability of an outcome on any other toss. If we define heads as a success, and then P is the probability of a head and is 0.5 on any toss. The number of heads in n tosses is a binomial random variable x. The probability distribution of x is called binomial distribution. So the count x of successes in binomial setting has binomial distribution with parameter n and p, where n is the number of trials of the chance process and p is the probability of a success on any one trial. The possible values of x are the whole numbers from 0 to n. Not all counts have binomial distribution, as we are seeing in other examples, and be sure to check the conditions for a binomial settings and make sure you are being asked to count the number of successes in a certain number of trials. So for the binomial coefficient, there are a number of ways of arranging k, that is successes, among n trials. So it is written normally as this, and we call it n choose k. So when we explore it, it will be n factorial divided by k factorial and multiplied by n minus k factorial, where k is 0, 1 to n, that is the whole number. So I already told you that nk is, how we read it, we read it as n choose k. Exclamation sign is factorial. And it's saying n choose k is not same as n divided by k, and we already know this thing. So factorial is, if n factorial is there, so what we will do, n multiplied by n minus 1 multiplied by n minus 2 multiplied by so on, and the last would be 3 by into 2 into 1. So for the factorial 4, what we will do, 4 into 3 into 2 into 1. What's the value? 4 3 is 12, 12 2 is 4. So it's 24. But there is one thing, if there is 0 factorial, the value will be 1. So now here is the binomial coefficient example, and it's saying in how many ways we can 2 successes and 3 failures arranged in 5 trials. So it's just saying if S is success, and we know there are 2 successes and 3 failures. So total number of trials are 5. So it's saying it could be happen that there are success, success, then failure, failure, failure. It could happen that success, then failure, then success, then failure. So these are 10 possible arrangements from this 2 successes and 3 failures. So if we use the formula, that is 5 choose 2, we will take 5 factorial divided by 2 factorial multiplied by 5 minus 2 factorial. So what we will get? We will do the calculation and the answer will be 10. So we already know that there are 10 ways. What we saw here, we got from the formula. So binomial probabilities. Question is, if probability of success is P, that is equal to 0.8, what is the probability of the arrangement? Fs, Fs, F. So the probability of success, we already know it's P is equal to 0.8. Probability of failure, because there are only 2 outcomes. So we already know if there are only 2 outcomes and the probability of one is 0.8, what would be the probability of the other? It would be 1 minus P. So the probability of failure is 1 minus P, that is 1 minus 0.8, that is equal to 0.2. And we know that there are total number of trials are 5 and trials are independent of each other. So we can use multiplication rule because these are independent events, and if we have to find the probability of this arrangement, we will multiply all these because we know there are 2 success and 3 failures. So it's 0.8 square and 0.2 cube. Now question is, what is the probability of SSFFF or SFSFF? So in the last example, we got all 10 arrangements. These are all 10 arrangements. So these are all disjoints. As we can see in the question, it's written OR. So what we will do, we already know that if there are 2 success and 3 failure, we are getting this formula answer 0.8 square and 0.2 cube. And because they are disjoint, we can add them. And after this, we know there are 10 values, so we can also write it like this. That is 10, 0.8 power 2, 0.2 power 3. That is, and we earlier seen that for this 10, we can also write it as 5 choose 2. And now if we substitute the symbols on this equation, what we will get? This is 5, that is the number of trials. K is the success. So how many success? Because that is the we are looking for. So it is 2 in every outcome we can see here. So it would be 5 choose 2, that is NK. Then P, probability of success, power kth, that is the 2. Probability of failure, that is 1 minus P, what its power? N minus K. And this is the binomial formula. So now we know our formula, and now we will understand it by an example. So binomial probabilities, probability of K success in N trials with success probability P. So probability X equal to K equal to N choose K, P power K, 1 minus P power N minus K, where K can be any whole number, that is 0, 1, 2, 3, 4 to N. Now example is, if N is equal to 6, that is number of trials, probability of success is 0.7. Then what is the probability where X is equal to 3? So we are going to get, because we know 6, there are 6 number of trials, and probability of K successes in n trials. So we are going to write 6, 3, that is nk, 6, choose 3, then 0.7, what its power, because we already know that it's 3, it would be 3. And now because there are only two outcomes, the other will be 1 minus 0.7, and what would be its power, because there already we know that there are 6 number of trials, and we already know that there are 3 number of successes. So what would it be? 6 minus 3, that is 3. So we will get the result, and it will be 0.18522. So now there's one other example, that is lost or damaged luggage. If the probability that a piece of luggage is lost or damaged is 0.01, what is the probability that in 10 randomly selected pieces of luggage, at least one piece is lost or damaged? So our P of success, that is our probability, is 0.01. Number of trials are 10 because we are selecting 10 randomly selected pieces of luggage. And now we want to know that at least one piece of it is lost or damaged. So we have to find x that is greater than or equal to 1. So if we can find probability of x equal to 0 and we subtract it 1, we can get its probability. So what we are going to do, we are going to write the formula values in that formula we earlier used, that is total number of trials 10, 0, because we got here x is equal to 0. Then what is the probability? It's 0.01, its power 0. Then 1 minus 0.01, power 10th. And when we will substitute everything, and what we will get, we will subtract it by 1, and we got the answer 0.0956. One thing that we want to see here is here we can see that we earlier learned that if 0 factorial is there, the value would be 1. So here we can see that value is 1. And this we already did in last week, and we in the discrete distribution, we have seen that if x is greater than 1, we can do this thing. So we have already done this last week. So I think you will be able to understand it now. Now binomial mean and standard deviation. So if a count x has the binomial distribution based on n observation with probability p of success, what is its mean mu? In general, the mean of a binomial distribution is mu equal to n into p. Here are the facts. Mean and standard deviation of binomial random variable. If count x has the binomial distribution with number of trials n, probability of success p, the mean and standard deviation of x are, mean is np and standard deviation is under root np into 1 minus p. These formula work only for the binomial distribution, so they cannot be used for other distributions. So now we will understand about the shapes of binomial distribution. Here we can see that number of trials are fixed, but our probability is increasing. So binomial distribution, if we want to see what its shape would be, so we can see here when probability is increasing, first it's right skewed, but when probability is increasing, it's getting more bell shaped. But when again the probability is increasing, then it's again skewed, but now it's left skewed. So bell shaped at probability equal to 0.5 for n that is greater than 4. Skewed for probability that is close to 0 or 1 when n is small. So now earlier we have seen that our number of trials were fixed, but probability was increasing. Now if we keep the probability same and number of trials are increasing, what's the shape of binomial distribution? We can see here, that is if n is equal to 10 and probability is equal to 0.66, then we can see here it is somewhat bell shaped but kind of skewed. And here again we can see now it's, as the number of trials are increasing, it's going towards bell shaped, more and more going towards bell shaped. So we can understand this. So in conclusion, we can say for small n, that is number of trials, value of probability near 0, shape is right skewed. For value of p near 0.5, shape is approximately bell shaped. For value of p near 1, shape is left skewed. Effect of increasing n, shape approaches normal distribution as n increases, and in conclusion we can say the closer probability is to 0 or 1, the larger n needs to be for shape to be bell shaped. So for the normal approximation, as n gets larger, something interesting happens to the shape of binomial distribution. And it's saying that suppose that x has the binomial distribution with n trials and success probability p. When n is large, the distribution of x is approximately normal with mean and standard deviation. Mean is n into p, where standard deviation is root np into 1 minus p. So as a rule of thumb, we will use the normal approximation when n is so large that np is greater than or equal to 10 and n multiplied by 1 minus p is greater than or equal to 10. So now we will see an example for normal approximation, and sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes but shopping is often frustrating and time consuming as a statement. So suppose that exactly 60% of all adults US residents would say agree if asked the same question. And let x is equal to number of samples who agree. Estimate the probability that 1520 or more of the sample agree. So verify that x is approximately a binomial random variable. First we will check for that. So there is success, that is agree, failure, that is do not agree. So there are two outcomes. These are independent. Because of the population of US adults is greater than 25,000, it is reasonable to assume that the 2,500 trials are independent of each other. And n is equal to number of trials are 2,500 because they asked to 2,500 adults. And s, that is the probability of selecting an adult who agrees, is probability equal to 0.60. So it is verifying that x is approximately a binomial random variable, and we have to check the condition for using normal approximation. For that we know that n into p, that is 2,500 into 0.6, should be greater than or equal to 10. Here it is 1500, and n into 1 minus p is again 1000, and both are at least 10 as we have seen earlier. We may use the normal approximation here. Now we have to calculate the probability for, here we know that our question was to estimate the probability that 1520 or more of the sample agree. So for this we can use normal approximation, and we know that n into p is 1500, standard deviation is 24.49. So z, we got the z value 0.82, and we got the result that what is the result? It's 0.2061. So we can say that 20%, almost 20% people are agree. So for the sampling distribution of a sample proportion, there is an important connection between the sample proportion p hat and the number of successes x in the sample. So p hat is equal to count of successes in sample divided by size of sample. So we can write it as x, that is capital X, divided by n. So sampling distribution of a sample proportion, when we choose an SRS of size n from a population of size capital N with proportion p. So p hat is the proportion of the sample, whereas p without hat is the proportion for the population. Let p hat be the sample proportion of successes. Then the mean of the sampling distribution is p. How we are getting this? Earlier we have seen in the example when we were getting from the distribution, sampling distribution of x bar, we were getting the value mu is equal to x bar. Similarly here we can see that p hat In the p hat, we can see here it's x divided by n. In this, x is binomially has a binomial distribution. So in the binomial distribution, we have seen what is the mean formula. It is NP. So we can see when we write NP divided by n, we will cancel out n. Then what we will get? Only p. So here it is saying that is just a derivation. So if you don't want, then you don't need to understand that. But you have to learn that or understand that the mean of the sampling distribution is, because here we are talking about the sampling distribution, and the mean of the sampling distribution is p. That is size n with proportion p. That is similar with sampling distribution is p. When we talk about the standard deviation of the sampling distribution, it will be root p multiplied by 1 minus p divided by n. So it's saying for large n, that is if number of samples are large enough, then p hat has approximately the normal distribution with mean p and standard deviation root p into 1 minus p divided by n. As n increases, the sampling distribution becomes approximately normal. So in this figure, we can see here the standard deviation is root p into 1 minus p divided by n, whereas mean is p. And here we can see here the values of p hat. So now we will understand about the Poisson settings. And frequently we meet counts that are open-ended. For example, the number of customers at cafe between noon and 1 p.m. Number of dings in your car door. The number of reported pedestrian bicyclist collisions on campus during an academic year. So here a Poisson settings arises when we consider the number of successes that occur in a fixed unit of measure, such as period of time or region of space. So for the conditions of the distribution, first is the number of successes that occur in two non-overlapping units of measure are independent. Second, the probability that a success will occur in a unit of measure is the same for all units of equal size and is proportional to the size of the unit. And the probability that more than one event occurs in a unit of measure is negligible for a very small sized units. In other words, the events occur one at a time. Now the Poisson distribution. For the Poisson probability, if capital X has the Poisson distribution with mean mu, the possible values of X are 0, 1, 2, 3 if K is any whole number. So probability is equal to E to the power minus mu multiplied by mu to the power K divided by K factorial. Now I just want to say one thing, that in the Poisson mean and variance are equal, and generally here in the book it's represented by mu, but generally it is represented by lambda, because to show that they both are equal. So if you Google for the Poisson probability, you will get it lambda. So this is the same formula, but our symbols are different. And what is mu here? Mu is the parameter. Mu is the mean number of successes per unit of measure. So now we will see an example. Suppose the number of dropped calls on your cell phones varies with an average of 2.1 calls per day. And if we assume the Poisson setting is reasonable, we can model the daily count of dropped calls X using the Poisson distribution with mu 2.1. What is the probability of having no more than 2 dropped calls tomorrow? So here, if we have to find the probability of no more than, so it should be X less than or equal to 2. So we will get the probability of 0, then 1, and then 2, and we will add it. So we are going to apply the same formula we got, and here when we use all the put all the values, what we will get, it's 0.6497. So here we can say that 65% roughly chance that you will have no more than 2 dropped calls tomorrow.